All right, and we're back. Day two. Day two. Okay, so what we're going to look at today, we're going to look at free body diagrams specifically. Some quick review. All right, our types of forces. We've got a few important ones. Let's go with blue. Let's get crazy today. All right, so when we talk about forces, the big ones that we really need to worry about, Fg, Fn, gravity, normal, friction, which we're going to break up into the flavors of static friction and kinetic friction. That's going to help us out a little bit later. All right, we got normal force. Oh, I already said that one, sorry. And then this one for spring, but I'm just going to say spring right here so that we kind of keep tabs on the difference. And I feel like I'm forgetting one. Oh, tension. The force of tension. Otherwise, sometimes they're called just plain T. Just depends on who's writing the question. These are the biggies for us. Now, there is another one that we should mention, and that is centripetal force. All right. Um, the reason I didn't bring it up yesterday is I didn't want it to get muddled up with these other guys because it's important, but it's not exactly the same sort of force like these are. We just finished looking at centripetal acceleration. Remember that? We said, yeah, it's v squared on r. And accelerations, in this case, if we were talking about uniform circular motion, if you're moving in a circle and you're not changing your speed, the reason you're accelerating is because you're changing your direction. Still true. Still true, but all accelerations are caused by forces. Like say if you have an unbalanced force, it changes your motion, it changes your velocity. That's a fancy way of saying it makes you accelerate. So if we are dealing with a centripetal force, which is F sub c, that is going to be equal to, just like Newton's second law, instead of ma, we're going to say mac, right? Which means we could actually come up pretty quickly with this as a formula for centripetal force. But here's the crazy thing about centripetal force. It's always caused by another force. And I think I may have mentioned that already. All right, so I don't want you labeling these free body diagrams we're talking about with centripetal force as a separate arrow, okay? If something is moving in a circle, I should really define that, shouldn't I? That makes something move in a circle. It is being caused by something else. So for example, let's say you are a pair of jeans and you are in the washing machine, right? When you open the washing machine and it's all said and done, those jeans are going to be splatted against the wall of the washing machine. That's just how that goes, right? The reason is because as it spins, your jeans want to move in a straight line, right? If you are in, let's say that's a bird's eye view of the washer, right? And here's the pair of jeans, all right? As the thing starts to turn, let's say it goes that way. At any point in time, the jeans want to move tangent, right? We looked at how things like to move. They like to move in tangent lines based on their velocity as they progress around. But as they get ready to head off this way, the wall hits them and prevents them from doing so. And it happens at every point along that circle. The force is actually inward, like this, but it's our centripetal force. But what is it really? It's really the normal force. It's the normal force of the wall. But it's inward, therefore we call it a centripetal force. And that's actually going to be really handy because later when we do calculating and we need to figure out what the normal force is, we can set it equal because we know it's causing it. All right, usually it's a tension force or it's a normal force. Sometimes it's a spring force in some wackadoo sort of situations, or if we're talking about planetary motion, it's gravity that causes it. But it's always caused by some other force. So please don't ever put down centripetal force on a free body diagram like an arrow all by itself. Okay, so it doesn't work like that. All right, what I want to focus on today are what are known as free body diagrams, or sometimes force body diagrams, but I call them free body diagrams. All right, so what we're going to do is we're going to take any body, regardless of how large and irregularly shaped and so on, and we are going to shrink it down to a dot. Or what I tend to do is make it into a box, or you can make it into a dot. And then you're going to use arrows to show the forces. And then you label them. That's pretty much what free body diagrams are all about. What I do want you to understand is that they are snapshots. They are not considered over a long period of time. They are just like if you took a picture, you freeze time. So look at what's happening, freeze time, draw the arrows of what the heck is going on. All right, so some easy ones. Let's do some easy ones. I'm all for that, right? All right, if we have a box at rest on a table, here's my box, or you could just do dot, up to you. There's my table. What's going on here? Well, I've got gravity going down, right? But I know it's not sinking through the floor. There's got to be something on its way back up. Hopefully you've guessed it. It's going to be normal force. And that's it. That's my free body diagram. Now you might say, well, but there's friction, right? Because it's resting on the floor. And so I've got to have some friction. So if I had this one and this one, then let's say we have friction going that way. But it's that static friction you were talking about, Mrs. Grady, because yeah, it's at rest. And I would say, you know what? That sounds like a great idea, except now look what you did. All right, you have an unbalanced set of forces. What is that object doing? It's accelerating. It's changing its motion. And if it's at rest, no, it's not. So, no. Friction is tricky. I'm not going to lie. Sometimes friction can really get us. All right. It's not that friction can't cause something to accelerate. It does occasionally. However, if it's at rest, you shouldn't be accelerating. You shouldn't be changing your motion. So watch out for something like that. If you are pushing on a box, but it's not moving, then I would say, yeah, okay. Gravity, normal force, because it's still on the floor, right? It wasn't terribly specific here with my example, but you get the idea, right? I'm pushing on the box. Now you might be tempted to do this, and it's not technically wrong, but you know, if you want to say you're pushing it to the right, we usually write the arrows as if they're coming from the center, and they're really going this way. And depending upon what kind of who wrote the question, I personally call that a normal force because you know you're pushing, but what some places they tend to call it an applied force. I think you kind of got the drift, right? You're pushing on it, so it's an applied force or a push force or a thrust force. Those are all good names for them. It just depends on what you want to call it, but I usually go with normal force. Well, in this case, if it's not moving, this can't be my free body diagram again because I have an unbalanced set of forces. I must have a fourth force. This is when I'm going to have some friction, or if you want to call it F sub S for static friction, that works as well. I don't really care which one you use. Okay, but that's balanced, which tells me it's not moving. Now, here's the thing. When you look at a free body diagram, do not be fooled. Arrows do not tell you where the motion is, and arrows do not tell you what direction the motion is. All right, so that's something to also keep in mind. I'm going to put it in a different color so it stands out a little bit more. But FBDs do not tell the direction of motion. MOPS is going to try to fool you. I'm not going to lie about that. And if you did MOPS last year, these were some of the most frustrating ones because you would look at the free body diagrams and you'd say, it's got to be moving to, which ones could be moving to the right? And you're like, well, this one has an arrow to the right. It must be moving to the right. No, this is telling you the forces. This is not telling you the direction of the motion. Okay, this one over here with the 4 arrows, this could be an object at rest, or it can be an object moving, just moving with constant velocity. It could be moving up with a constant velocity. It could be moving down with a constant velocity. It could be moving left or right with a constant velocity. Just those arrows don't give you that kind of information. So make a big giant note to yourself that you cannot tell the direction of motion. Period. End of story. What you can tell from balanced and unbalanced forces is which way you will accelerate, which way you will change. If you have an arrow over to the right and there's no arrow to the left, you are changing or accelerating to the right. That could mean you're getting faster and moving to the right. It could mean you're getting slower and moving to the left. Again, you cannot tell without more information. So do not overestimate what these things are going to tell you. Okay? Free body diagrams do not tell you direction of motion. They just don't. We all want them to think they do, but they do not. Okay, let's try something a little bit different. Let's say you have something and it is hanging from the ceiling. All right, so this is a pretty typical one, right? You've got some box. Actually, that looks like a bug now, but you know, you've got some sort of a box and it is hanging from ropes from the ceiling. What does my free body diagram look like there? Okay, there's my box. Gravity is always present. Always. Every single time. Since these are ropes, there's going to be tension. You can call it FT or you can call it T. And that is not even in any way, shape, or form, but oh well. All right, what's going to matter, of course, are the angles here. If the angles are equal, you can tell that the tensions are equal. If they're not, they're not. And the math just gets a little more difficult. All right, but notice what's not here. You know why? Because it's not sitting on anything. You cannot have a normal force if you do not have a surface. And don't tell me, oh, but the ceiling is a surface, because all I care about is the box, okay? And the box ain't touching the ceiling. So no normal force there, peeps. All right. Now let's try something also a little more difficult. Draw this steep, you guys. Let's draw an inclined plane. Let's say there's a box on an inclined plane. And I don't know, let's say it's attached to a rope and there's a pulley. Good enough. All right, what kind of forces do we have? All right, so think about it for a second. I'll even wait. I'll pause and then think about it. Try to draw. You know, maybe Doc will pause the tape here for a second and give you a second to give it a try. Work in pencil. All right. Okay, so hopefully this is what you came up with, or at least something like it. Gravity's got to go straight down. Right? Tension has got to go along the rope. Normal force. You know, normal force people usually get a little wonky with, right? They want to put it this way. They want to go like that because it's, you know, it's opposite of gravity. But don't be fooled. That's not it. Oh, I lost my whole thing. All right, I'll have to draw it over. I'll draw exactly the same thing over in a minute. This is kind of fun, I'm not gonna lie. Drawing all these little colory things. All right, so I had tension going this way. Normal force has to be perpendicular to your surface. It should look like that. Now, before you say to yourself, well, that doesn't look very balanced. You're right, it doesn't. But we are going to take our objects and we are going to break them up into components in a little bit. Okay, so no worries, no worries. We will analyze these a little bit later. The main thing I want you to keep in mind when we deal with solving some of these problems is what I like to, now, again, these are just Grady words. This is just how I like to describe it. Okay, if we are dealing with something that is balanced forces, I like to say that all the forces pointing to the left have to equal all the forces pointing to the right. And all of the forces going up have to equal all the forces going down. All right, that's when we are what's known as equilibrium, or I like to also call it balanced forces. All right, so up equals down, left equals right. These are the main premises that I go with. All right, when you have things that are on the diagonal, it gets a little tough to figure out, well, I mean, look at this guy. Is that left? Is that right? I don't know what that is. Well, that's where we start making triangles out of stuff. And we break it up into left and right. That way we can actually solve what we need. Okay, so even though this looks a little bizarro to start with on my inclined plane, don't be fooled, don't be worried. We're going to make some triangles out of that, and it's going to work out just fine. It's going to work out just fine. All right. My last crazy looking one I'm going to show you is something called an Atwood machine, and we see a lot of these when we do physics. It doesn't have to have a ramp, but it often does. And there's a pulley, and then there's something else over there. All right, this is what's known as an Atwood machine. You've got your pulley there. It's going to help change the direction of the rope. And there's a lot of variations here. Like sometimes they look like that, and sometimes they add another block or two or three. It can get complicated, right? Or you could even be going, skip the ramp altogether, right? You could have something that looks like that. That's technically what we call an Atwood machine as well. The function of the pulley is to change the direction of the rope. The nice thing is that right now, with what we're studying, we are going to ignore the pulley. That won't be forever, but for now, we're going to ignore it. The questions will usually say something like, it's a massless pulley. And there's really, of course, no such thing, but we're ignoring it for now. And we're just going to work with something that is a very low friction, light pulley that is not going to change the tensions in the ropes. Okay, so for now, we'll ignore those. I'm going to show you how to solve those in a bit. Okay, so no worries there. What I'm going to do is I'm going to take this example right here, and I'm going to take this example right here, and I'm going to show you one with some numbers to kind of give you an idea as to how to solve them. And maybe I'll do one of these too. To see how much I feel like doing right this minute. All right, but we'll start with a couple of simple ones. We'll start with some statics, and then we'll work our way up to some of the more complex sorts of free body diagrams and how to analyze those. So hang on a minute, and we will get right there. Okay, so here's what I want to do. I am going to go over basically how you set up an object on an inclined plane. I'm going to set up something in a hanging from a ceiling, and something with more than one object. And then I'm going to have you practice with a series of examples that I have already set up, and I already have the solutions in a different video, so you can check those out. Okay, so here we go. Let's do one where we are dealing with tensions. Okay, so let's say you have something hanging from the ceiling, and I don't know, you can make it like 100 kilograms, and it's hanging from the ceiling. And let's say that my angle's 30 degrees, 30 degrees. We have the same angle on both sides. I know that's very tough to read. I apologize. 30-degree angles for both. All right, I'm trying to reach over my head, and that's an issue. So if you draw the free body diagram, gravity is going to be pulling you down, right? And then you have tensions going this way. You want your tensions to be going up, because quite frankly, if your tensions were pointing down toward the dot, this thing would crash into the floor, and it is not doing that. So you definitely want to make sure. I'm going to make that a little longer so that I can draw something in a relatively straight line. Okay, so 30 degrees here, 30 degrees here. Your free body diagram does not have to include the ceiling. I'm just doing this because I'm going to show you how to break it up. So when you do the free body diagram, this is it. All right, you could call it tension 1 and tension 2. That's fine. Free body diagram on an AP exam, they are basically going to have a special spot for you before you start doing any math work and say, draw the free body diagram. And the main idea is that you want to just put in the forces that are acting on the block, nothing broken apart. Okay, so this is what it would look like. This would be your answer for a proper free body diagram. Now I'm going to take it and I'm going to maul it and make it into something totally different. Okay, because I'm not going to be able to solve for anything unless I, take this and break it apart. Okay, because we can tell right away that the forces are balanced. All right, we have balanced forces. Sorry, that's what that means. All right, so we have balanced forces because we are at rest. What this tells me is that left equals right, forces up equal forces down. All right, so mathematically I can work with this. All right, but I can't work with this in the condition that it is, because if you look at T1 and T2, they're not left or right. They're not up or down. They're a little bit of both. So we're going to have to make the triangles out of those. Therefore, we can have left and right pieces. We can have components. And this is why we did vectors in chapter 3. So we could do something like this. Okay, so let me show you what it's going to look like when you go to do the math. And I'm going to do some quick math here. And I'm going to cheat and use 10 for little g. All right, so if this is my stuff, right, and it's 100 kilograms, Fg is going to be mg, right? We did cover that, didn't we? I hope. Oh, I think I forgot that part. I apologize, guys. I'm getting distracted here. All right, so just a thought. I'll put it over here so you have some words. I'm sorry. I think I've covered stuff, and then I forget. I did this in general physics. Force of gravity is a fancy way of also saying an object's weight, which is not the same as its mass. But what we're doing is we're taking Newton's second law and we're applying it specifically to gravity. And let's face it, the acceleration due to gravity is little g. So that's where this is coming from, right? We also can consider it a ratio between the mass and the force, and we could figure it out experimentally, which those of you who are in general physics with me already have done. All right, so if I take 100 kilograms, and I'm just going to cheat here and say 10 meters per second squared, so I don't have to bust out a calculator because I didn't, bring one with me. So it's roughly 1,000 newtons going down. So this Fg is going to be 1,000 newtons going down. Okay, so now let's talk components and breaking this bad boy up. All right, so 30-degree angle, 30-degree angle. It's pretty straightforward. It's pretty easy to see that these two tensions have got to be the same because the angle is the same. But here's how I'm going to deal with it. I'm going to make a triangle out of it. And I can put the triangle out here just because it's easier for me to draw and have the space, okay? Alternate interior angles tells me that these are 30 as well. Thank you, geometry. All right, I tend to call these X and Y because they make sense to me, right? I'm in the Cartesian plane, and I can just call those X and Y. Now, if I want to look at it this way, now left equals right, up equals down can make total sense to me, right? So Tx has to be equal to Tx. Now, granted, I know they're the same because my angles are the same, but this fulfills left equals right. And I'm just going to let that go for now because I don't really care about those particular guys, right? If my angles are the same, I don't have to do anything fancy because my angles, are because they don't match. All right, but it's the up equals down that I find the most intriguing. So if I do forces up equal to forces down, well, forces up, I have 2ty. They're both literally pointing up. And this is Fg. So I could say 2ty equals 1,000 newtons. Ty equals 500 newtons. So if I put that up here, I know it's the same on the other side, but all right, so we'll put that one over here. And then we can use trigonometry and figure out t, which is the hypotenuse, right? Super simple. So yeah, all right, so sine theta or sine 30 equals my opposite side over tension, which is my hypotenuse, which is what I want. So tension will equal 500 divided by the sine of 30, which as we know is 1/2, which is the same as multiplying by 2. So each of the ropes, voila, 1,000 newtons. Now don't be fooled, that's not for every single one where it's like the same as the gravity. It's just because I made it a 30-degree angle so that I wouldn't have to pick up a calculator because I was being lazy. So important lessons to learn. Take things on the diagonal and break them up into left and right components. Don't assume in a tension problem that your tensions are double or the same value as the gravity. It's not the case. It's only when it's a 30-degree angle. All right, remember, left equals right, up equals down if something is not moving or it is moving with a constant velocity. That is what we consider to be statics. Okay, so that is what you're going to do for a tension problem. Now, if your angles are not equivalent, here's what's going to happen. You're not going to be able to solve it because you're not going to have enough information. You're not going to be able to say this. If your angles aren't equal, you can't do what I just did there, and this part I underlined in blue isn't going to work. these are also, they're going to be equal, but they are not going to have the same angle. So you're going to have to use a system of equations, and you're going to come up with some new expression over here, and you're going to put it down in there. FYI, we're not quite there yet. Practice some of that a little bit later. You can try it out. Okay, but for now, we're good. We're good. All right, next, let me show you an Atwood machine. Let's show you how to break up an Atwood machine. Or not an Atwood machine, I'm sorry, an inclined plane. I'm going to draw it pretty steep. You should too. I think it helps. Here's your box. Let's put in gravity, normal force. All right, and I'm just going to put a tension force on here. Let's pretend that we've got a rope. Okay, so we've got 3 forces. When you get ready to do something like this, now usually what I would do is I would be standing in front of you with the document camera and I would literally turn the paper. Okay, so what I would do is I would turn the paper like this, and it would look like this. And the reason I would do that is because I want you to see why we're going to take gravity and make it our triangle. Okay, if we look at the Cartesian plane, and the reason I'm shifting the Cartesian plane is because which way would we accelerate? If the rope were cut, we would accelerate down the hill this way, wouldn't we? So I'm shifting the Cartesian plane so that it falls along where the acceleration would go. It would go that way, right? If I look at it this way, then gravity is my diagonal. That is the one I'm going to break up into a triangle, right? Because that's the one that's going to be the sideways wackadoo vector for me. Doesn't look like it at first, but it's easier to see it if you can turn it and actually tilt it and see it. Now, I don't want you to keep it like this. I don't want you to keep it in this way because it's going to get confusing when you go to do it and grade it and all that sort of stuff. But it gives you an idea of why gravity is always the one you're going to break up. All right, now, hopefully you've got this down. I'm going to erase it so that I have some room to work because I kind of need some space. All right, but hopefully that made some sense. All right, here we go. Now, since normal force and tension force are in like the up, down, left, right kind of direction, gravity, on the other hand, is not. And I'm going to make a right triangle out of gravity. Okay, so whatever's on a diagonal is what you're going to break up into arrows going up, down, left, right. If you consider, I got to make this a little bit longer here. If you consider, I don't know, let's say this is 20 degrees. This angle is 20 degrees. They match. They always match. And the reason is because they're similar triangles. And if you don't believe me, take FG and extend it down and make a right triangle, and then you'll have a 20-degree angle and a 90-degree angle right there, and you can do the math here and find this angle, and then you can do this and find the whole one, and lo and behold, that's going to be 20. Like every time. So you can either believe me out of the gate, or you can do the geometry every time. It's totally up to you. I don't care, but it's going to waste time. All right, this always matches this every time. Now, also what will happen, because this is my hypotenuse, FG is my hypotenuse, this is going to be FG sine of theta. Although realistically, and you are AP level, I wouldn't call it FG, I'd call it MG, because usually when you're doing these problems, you have more than one object and you have to distinguish them as M1, M2, M3. So perhaps the habit of this instead is a better habit to be in. All right, and this is going to be mg cosine of theta right here. Okay, that's how you break up an inclined plane. Now, let's assume we're at rest. There's all sorts of twists on these problems, right? But let's assume at this point we are at rest. So when I consider forces up equal forces down, what is pointing up, literally up? A normal force. What is opposite? This one, mg sine theta. I'm sorry, mg cosine theta. All right, those are going to be equal and opposite. This is why the block is not levitating off of the ramp or dropping through it. Okay, when you look at left and right, And you know, the old way of saying it is the sum of the forces is 0, and that's still great. You're going to see that on some of the old, you know, AP exams and stuff, but I still like to break it up into the different possibilities. All right, so don't be thrown. This just means the sum, right? It's a sigma for sum. Sum of the forces is 0. They're balanced. It's a fancy way. Well, actually, it's a shorter way of saying that they're balanced, right? Okay, so what's going to the left? This one. This one's going to the left. That's my left that I'm calling it anyway. So, oh, shoot, not F. mg. I have such bad habits. I can't believe they put me in charge of you guys. Right? So mg sine theta equals, and what's going up the hill? Tension. Ooh, what about friction, Mrs. Grady? I don't know. I gave you a frictionless one this time. If you had friction, you know, it'd be on one of the other sides, just depending on which way it was going. Okay? But this kind of technique is what we're going to use each time on an inclined plane. Now, what if we had an Atwood machine instead? Right? We've got this, and we've got this, and then we've got this, and then we've got, oh no, there's another one. Okay? Now, here's my advice for an Atwood machine. 2 objects, 2 FBDs. If you've got 3 objects, then 3 FBDs. 4 objects, 4 FBDs. You get the gist. There are ways to shorten and condense that. I like to do them one at a time and sequentially put them together. That to me works in my brain the best. So that's how I like to teach it. If you like to do it the other way, figure it out, be my guest. Go ahead. All right, so this one, it looks like that. So I'm not redoing that. All right, this one over here, like we call that M2, you're going to draw a second free body diagram for that, right? M2G, that's actually a better way of saying gravity. Instead of saying FG, say M2G because it's specific to that mass and it shows you that. And then this one would be tension. And the cool part is that this tension right now equals this tension. So if you can figure one of them out, you know the other. But that's only because we're ignoring the pulley. All right, I hate to break it to you, but we're not always going to ignore the pulley. But we won't do that till after Christmas. So for now, we can just pretend we're always going to ignore the pulley. All right, so for right now, my tensions are going to be the same. They're going to be the same. And just for future reference, if it's not at rest and there's an acceleration, the accelerations will also be the same. That might be something you want to write down and kind of put to the side for later. Okay, so when we're dealing with an Atwood machine, if we are ignoring the pulley, tensions in the rope connecting the 2 objects are going to be identical. Acceleration of the system, if it's accelerating, is going to be identical. So that might be something to consider for later. Okay, now at this point, I am going to send you over to the other set of worksheets where you can start to practice, and you can do that together as a class, do them one at a time, use the video for later, or maybe Doc wants to assign it for homework. I don't know what the time frame is at this point, but I definitely want you to practice the free body diagrams and starting to solve for some of these forces. Maybe you want to work on in whiteboards. There's a whole range of possibilities here. I think together is better personally, but I'm going to leave that up to you guys. In any case, hopefully this was helpful.